In September 2008, a tiny team stood on a remote Pacific island facing total bankruptcy. 3 consecutive rocket launches had exploded. If Flight 4 failed, SpaceX was dead. What followed became the most disruptive revolution in spaceflight history. For 6 decades, space travel was dominated by government monopolies and cost-plus defense contracts. Throwing away multi-hundred-million-dollar rockets after a single flight locked orbital payload costs at an astronomical $10,000 to $20,000 per kilogram. NASA's Commercial Orbital Transportation Services program gave SpaceX its lifeline. By applying Silicon Valley fast prototyping and vertical integration, SpaceX promised to deliver cargo to the International Space Station at a fraction of traditional costs. Falcon 9 redefined launch economics, driving payload costs down to $1,500 per kilogram. Competitors like United Launch Alliance and Aerospace found their legacy architectures suddenly priced out of the commercial market. Reusability created a self-reinforcing flywheel. By flying recycled boosters, SpaceX could launch thousands of Starlink satellites cheaply, building an orbital broadband constellation that funds next-generation rocket development. By 2024, SpaceX was launching over 80% of all global mass to orbit. A single private company was out-launching every nation-state on Earth combined. Over 15 years, SpaceX iterated the Merlin engine continuously. Thrust increased from 300 to nearly 900 kilonewtons, while cooling evolved from ablative throat liners to regenerative liquid fuel jackets. Weighing under 400 enterprise kilograms while producing nearly 100 tons of thrust, the Merlin 1D achieved a thrust-to-weight ratio exceeding 180 to 1, the highest of any rocket engine ever mass-produced. Arranging 9 Merlin engines into a circular Octaweb layout transformed booster safety. If one engine fails in flight, the remaining 8 compensate instantly, giving Falcon 9 true engine-out capability. RP-1 kerosene leaves soot and coking deposits inside engine turbines during combustion. Cleaning soot required intense turnaround labor between flights. To build a rapidly reusable rocket, SpaceX needed a cleaner fuel. SpaceX chose liquid methane and liquid oxygen, methalox. Methane burns cleanly without coking, expands easily for autogenous tank pressurization, and can be synthesized directly on Mars via the Sabatier reaction. Raptor utilizes full-flow staged combustion, where separate preburners vaporize all fuel and oxidizer into gas before entering the main chamber. Before Raptor, FFSC engines had only ever run on ground test stands in the Soviet Union and America. Raptor 1 operated at 250 bar. Raptor 2 stripped away exposed plumbing to reach 300 bar. Raptor 3 reached a mind-boggling 350 bar, generating 280 tons of thrust per engine. By 3D printing internal fluid channels directly into the engine structure, Raptor 3 eliminated heat shields and complex external tubing, producing a sleek engine designed for rapid robotic mass assembly. Returning a rocket stage from hypersonic speeds requires hypersonic grid fins made of titanium. Actuated by hydraulic systems, these grid fins steer the booster through extreme atmospheric reentry forces. When boosters lack propellant to fly back to land, autonomous drone ships station hundreds of miles out in open ocean. Utilizing GPS thrusters and ocean wave compensation, boosters touch down within meters of the target center. Falcon Heavy combines 3 Falcon 9 booster cores to generate 5 million pounds of thrust. Seeing 2 side boosters touch down side by side in simultaneous sonic booms remains an iconic image of modern rocketry. To maximize payload to orbit, Starship's Super Heavy booster does not carry heavy landing legs. Instead, The orbital tower's massive steel chopstick arms catch the 200-ton booster midair as it hovers over the launch pad. Starship re-enters Earth's atmosphere horizontally at Mach 25 using 4 mechanical flaps to belly flop like a skydiver. Seconds before impact, Raptor engines reignite, flipping the ship vertically for landing. In the mudflats of Boca Chica, Texas, SpaceX built Starbase, a sprawling rocket shipyard operating around the clock. By combining steel mills, engine assembly, and launch pads in one site, design changes ship in days rather than years. SpaceX originally planned to build Starship from carbon fiber. However, carbon fiber costs $130 per kilogram and cracks under cryogenic liquids. Switching to stainless steel dropped material costs to under $4 a kilo. The Super Heavy booster is powered by 33 Raptor engines, generating 16 million pounds of thrust. It is the most powerful rocket ever built, producing double the thrust of NASA's historic Saturn V moon rocket. From Falcon 1's inaugural flight in 2006 to Falcon Heavy in 2018 and Starship orbital flight tests, SpaceX moved at an unprecedented cadence, completing over 400 missions. During hot staging, Starship reignites its vacuum engines while still bolted to the Super Heavy booster. A stainless steel vented ring channels extreme exhaust gas away, maintaining continuous acceleration during stage separation. NASA selected Starship HLS to land American astronauts back on the Moon for the Artemis III mission. Multiple Starship tankers will fuel a specialized moon lander in low Earth orbit before sending it to the lunar South Pole. To carry 100 tons of payload to Mars, Starship requires cryogenic refilling in space. Docking 2 ships tail-to-tail allows liquid methane and oxygen to transfer in microgravity. The ultimate goal of every engine, grid fin, and stainless steel ring is to build a fleet of 1,000 Starships capable of transporting 100,000 people to Mars during every biennial planetary alignment. By mastering rocket engine physics and proving that orbit is not a one-way trip, SpaceX transformed space from an exclusive national frontier into an open industrial highway.